So for the next track, we have several very high-quality presentations too, and I firmly believe that you will be quite interested in all of them. Not only are they great presentations with very good content, but they also have very good speakers too. And not any different from what you have seen so far. So this is no time to get on a low note and just wait for lunch. Get engaged. This is going to be a great track. Again, we are going to have now, to start the track on a nice high note, the team from our head Center for Collaboration for Data Analytics and Innovation in Germany. And this is, as I mentioned before, a collaboration between Elsevier, Humboldt, and HPCC. And this is the research that Professor Christoph Freytag and Fabian Fier have done in proximity search. And I find it very interesting. I hope you find it too. I think it gives us a nice edge on text analytics and some of even the things that Raj was mentioning about finding the potential for identifying documents that include copied material and others. So this is quite interesting. Please help me welcome Christoph Freytag and Fabian Fier to the stage. Thank you.
Well, now it's our turn. Thank you for having us, Flavio. Thanks for coming. My name is Christoph Freytag. I'm a database professor at Humboldt University in Berlin, and at the same time one of the two PIs at the so-called HEAD Center, which stands for Humboldt Elsevier Advanced Data and Text Center. So we are here as a couple. My doctoral student, who will later take over the hard part. I'm responsible for the easy part. And let me give you a little bit of my perspective on the last talk, which finished before the break. I'm a database person by heart. I've worked on this technology for 40 years, and when I say I'm a little bit disappointed how this technology is evaluated, I know what I'm talking about. I've worked on 3 products within the last 20 years with IBM DB2, not with it, but inside it, extending it. I've worked on SQL Server, and I've worked on the previous product of SAP called MaxDB. So I like to get my hands dirty. So in that sense, I'm probably not your average academician who likes to write papers only, but I want to see how systems are developed and how the ideas are used by real users. And so I think when we now come to new technology, we also have to think about how to adapt existing technology, and we also have to think about how new functionality is added. And this is what our talk will be all about. Namely, we think about similarity for many years, but getting similarity search and similarity joins scalable in our new environment, let it be HPCC, let it be MapReduce, that is a new challenge. And I think I would like to emphasize and give you some more motivation, because similarity is the basis for many things in the applied world. And so I would like to emphasize that a little bit more before then my student Fabian will talk about how we go about it to make similarity search really scalable. So let me start a little bit again about telling you about the HEAD Center. It has 2 separate branches, and we belong to the branch. One is the research integrity by a person who is not so much into computer science, and it's us, the core team, and we have already assembled several students around us doing work on what we call similarity search. So don't get me wrong, similarity search is an old problem, but looking at it with new technology gives us new challenges. And having a point of view coming from the database side, I always emphasize making it scalable. And scalable means not working on 1,000, not working on 1,000,000 items, working on 1 billion items or even more. And that's what HPCC is all about. So let me give you some examples. So we already heard this morning a quick word about plagiarism detection. think about it like a publisher, like Elsevier. They want to see how similar certain publications are. This is a big job, an ongoing job. So there are a lot of models, but very often it's very hard to implement it in a scalable manner. So this is coming from our partner who is very interested in determining when does plagiarism exist. Similarity is not sufficient. There must be hardcore criteria, and even if they are met, I think we also still need a person who looks at two similar documents and then decides, based on the appropriate community, whether or not plagiarism exists or not. So I don't think this is an automated process. It can only be supported on large scale by systems like HPCC. Let's take another example. If you look look through the web and you search for something, for example, like traveling. Sorry, this is partially in German, but you might be interested in some kind of area where you want to spend your vacation, and you find these kind of web pages, but really what you are interested in is saying, I want to go to Nepal, but with the kind of properties that are found in these on the other web pages. So rather than typing in all the criteria again, the system should be able to apply the already looked at properties and apply them to a new area like Nepal, and then go back and search. The other thing is, consider that you have looked for a particular arrangement and you find out it's booked out. Rather than starting your search from scratch, you really want to say, I want to find a similar travel arrangement similar to the one that I cannot book anymore. So rather than starting all your searches from scratch, the system in the background should somehow take whatever it can from the existing environment, from the existing context, and then apply it with new dimensions. This is no similarity. Well, it is something that is, according to, now you see a little bit of SQL, something that I would introduce into SQL with new kind of keywords, which does not exist, but this is somehow the vision. We want to say that we don't look for exact matches, but for similar matches. Why do I use SQL here? I strongly believe that declarativeness is one of the strong points, and it has found its way into HPCC, and it should continue to be there, not only in that environment, but into all kind of environments, and we heard already some examples this morning. So now it's for Fabian to continue on the hard part and to dive down into some ideas we have on the technical level. So please bear with us and understand that this is nothing that comes for free, but we really have to develop in order to make things scalable. So it's all yours, Fabian.
Thank you, Christoph. Let's go into the problem in a more formal way. So the problem statement would be, we have a set R of documents, maybe web pages, and we have a search document S. We also have a similarity function, something like this here, similarity of RS, which means like we want to compute a number between 0 and 1, which tells us how similar these two documents R and S are. So 0 means they are not similar at all, 1 means they are identical. We also have a similarity threshold theta. The user can choose that. And what we want to find is all documents within the big R that are above this similarity threshold. So how could we define the similarity function? There are various functions available. Let me just introduce one here as an example. It's a set-based similarity function. It's called Jaccard Similarity. So both documents here, R and S, contain terms. And as you can see with the blue background, they have three terms in common. We can also show this in this little diagram here. And the Jaccard similarity computes like the size of the intersection of both records divided by their union. So they have a similarity of 3/8. This is like 0.3 something, and that's not big. So for many applications, we search for something that is more similar, starting from 0.5 up to 0.9, whatever. It's very application dependent. So how could we actually compute this similarity? A naive approach would be, so given our search document S, our input data set R, and our similarity threshold theta, we could just go through all these documents and apply our similarity function to find documents that are similar to our search document. That's probably not a good idea. We are talking about big data here. This similarity function, or the similarity functions are usually quite expensive to compute, and users don't want to wait for a result forever, so that's not a very good approach. So this is not a new problem, as Christoph said before. There are various approaches already existing for that problem here, but we found that there are approaches from databases that are not applied yet, and we think if we apply them, we can do better than these approaches. So our approach is the following. We use distributed similarity join algorithms. When talking about distributed algorithms, we think of MapReduce algorithms. And what is a join? Join is a similar problem to the search. We don't use one search document, but we want to have all similar documents within one document set. So how can we use that for search? That's not very obvious. We use intermediate results for indexing. So all these algorithms have in common that they produce an intermediate set of data that we can actually persist and use for search subsequently. Our approach now is we are running experiments. We want to know the best approaches for the join case to apply these for search. So what are the approaches, the big ones? One is metric partitioning. So if we think of documents in a high-dimensional space, we can apply hyperplanes to divide that space, and we can do that iteratively until we get partitions that are small enough to fit into main memory. Since we are talking about text here, we have the curse of dimensionality. That does not work well with text data, so we are going to skip it here. Our focus lies on filter and verify approaches. Filter and verify approaches work in the following way. We generate a set of candidate pairs, and this set of candidate pairs is a superset of the result set. By the use of filters, we make sure that this superset is orders of magnitude smaller than the cross product, usually. Usually means if the documents that we are looking at are not very similar. In the next step, of course, we have to verify if these candidates are really similar. So we have to go through each of these candidates and verify if they meet the similarity threshold. One approach is to use an inverted index. We call this a full filtering approach. So we built an inverted index. An inverted index assigns each term a list of documents that it's contained in. Let's put it in a more graphical way here. So we have 3 example documents, and they contain these bubble terms here. And we can extract all the terms that exist, and we can actually assign links to the documents they are contained in. So this is our index. The index contains terms and references to the documents. How can we use that now for our similarity join problem? Well, we can go through each of these terms here in the index. And then we compute the cross product of the references within each term. And this is our candidate set, right? So we look at every pair within the cross product for each postings list, and look if the similar is above the threshold. Why is that better than a naive solution, the cross product, for example? Well, usually we exclude those document pairs that do not share at least one common term, right? So if two documents do not contain the same term, they cannot come up in our result, in our candidate set here. But still there's a problem if we have a term that is contained in all documents. So then we compute the cross product again, we don't win anything here. So that's a specific problem of that approach. But there are solutions for that. One solution is to apply another filter. This is called prefix filtering. I skipped the formula here. I just do an example how that works to give you a notion. Let's take these two documents as an example. Again, they have three terms in common, but now we can actually compute a prefix. This prefix is dependent on the similarity measure, it's dependent on the length of the record, and it's dependent on the similarity threshold we chose. And for the first record here, it's 5, so I underlined the first 5 terms in R. And for the second one, it's 4, so I also underlined these ones. And now you can see we have only one term matching if you only look at the prefixes. So the idea is now we only look at these prefixes, we index only the prefixes, and the result stays complete. This can be shown. This is a theoretical thing. I don't want to bother you with it. But the main point is we don't need to index the whole records for this problem to get a correct result. So think back to that problem. If we have a term which is in every record, how could we mitigate that issue here? Well, we can take the global term frequency and order each document by this frequency. So if we have the least frequent terms on the left side and the most frequent ones on the right side, and we only take the prefix of the least frequent ones, we don't run into the problem of actually having the cross product here, hopefully. That's already true for this example here, so we would skip the most frequent ones. So, as I said before, our approach is we want to find the best join approaches, and so we experimentally compare them. These algorithms are actually MapReduce based. I copied a little snippet out of a paper here. It says their approach is up to 30 times faster than the state of the art. This is how it looks like when we do it. So on the x-axis you can see different algorithms, and on the y-axis their runtime. And well, okay, this algorithm here is a little bit faster than the other ones, but we cannot really verify that it's like 30 times faster. So we have a comparability issue here. The runtime is dependent on many different factors. For example, implementation. Think of implementing a list. You can implement a list in a million different ways, and every way has its own good sides or bad sides. And it's usually not described in the literature. You have algorithmic parameters you can tune. You have system parameters, like the execution system, which is underlying, has certain sets of like standard values you can tune or even have to tune to make it work. Surprisingly, the problem statements also differ a little bit, which cause some problems. And as we already said, data can cause issues, like when you have very frequent terms, that's a problem for some algorithms, and you can mitigate it by just removing them from the data, but it's not really clear sometimes in the literature if they've done that or not and how they did it. So let's not talk about everything here. So our problem is like, how can we create a fair environment to compare these join algorithms? Let's look at two of these dimensions here, implementation and system parameters. What about implementation? So the most important thing in the implementation we found is to use combine. Combine in MapReduce means you have to reduce the size of the data on the sending side whenever possible. So you don't send it over the wire and cause some computation on the other side. If you can do it early, do it early. The same applies for the receiving side. I called it prune locally here, which might be a bit confusing. What I mean is, if you keep a state in an operator that gets a lot of data and the state grows, you have to make sure that it doesn't grow over the memory which is available. And so there are tricks sometimes you can apply for some algorithms, and it's very important. System parameters, I mean, for example, data split. The input data split on HPCC is, for example, when you spray, so it's evenly distributed amongst the nodes. On Hadoop, it's a bit different. It's usually the HDFS file size. Parallelization degree, you can choose how many reducers you have in the case of Hadoop. And of course, memory parameters. So we implemented these algorithms in Hadoop first and ran into these comparability issues because Hadoop has many of these parameters, especially the system parameters that you can tune. And so we're kind of stuck with this comparability issue. So our idea was use a MapReduce implementation with less tuning knobs. We found HPCC. HPCC is not originally a MapReduce system, but you can easily transform a MapReduce program to HPCC. So we did that and compared that to our Hadoop implementations. And so this looks like this. This is just an example. On the left side, you see a Hadoop program or two subsequent Hadoop programs, and on the right side, the corresponding ECR program. And so when you go back to these points I had before, when talking about implementation, it's also important to care about this combine issue here. So you also have to apply that in ECL. You also have to care about this, state problem when you when you keep a state within an operator. And but for the system parameters, it's quite different. The data split, for example, has a good default in HPCC because data is sprayed evenly amongst the nodes, which is usually okay. So it's also good for smaller data and a very compute-intensive job. Parallelization is handled by HPCC implicitly, which is also kind of a good default. I don't know if you're aware of the default parallelization degree in Hadoop. Does anybody know? It's 1. And memory we didn't look at in a detailed way yet, so we don't know yet. Okay, so this is where we stand now. We compare all these algorithms experimentally. And how does the future look like? We use these for search, as we said before. And now I want to give a little outlook. We talked about enhancing web search. We saw this example here. So the user finds a result, and web search is only textual, so there's no similarity search possible. We said, okay, it would be nice to really have a way to find similar websites from given one. But we also want to have a look at if we can filter these results according to further attributes, like we are used to it from SQL. For example, you can filter it by date, or here by availability, or location. So these are attributes from other domains, and it's very interesting to integrate these attributes into an index which is originally textual. That's quite an interesting research task, and I'm looking forward to work on that. So thank you for your attention. And if you have any questions, let us know. Okay. Love you.
We have 27 minutes left. Seconds left, sorry. No questions, so you can pick us up during the break. Thank you very much. Yes. Thank you.
Short on time. Thank you. Thank you. Very good. I don't know what you think, but this is what exciting. Some of the things that we were talking before about plagiarism detection, that's cool. The search, similarity search in web similarity search and document similarity, and I assume some of our, even within RELEX, some of our sister companies will be very interested outside of Elsevier, who is already very interested in this type of capability. So this was very good, and it's a good preamble for what we will come next throughout this research with HEAD. Now, as a preamble to the next talk, we have Itauma with our collaboration with Wayne State University. Itauma will talk about some unsupervised classification of images using HPCC. I think he had a poster as well. He is a very committed supporter of HPCC, has been doing a lot of things for us as an ambassador and speaking even in events for us. So we thank him really for all he has done and all he will be doing as well. Itauma, thank you very much, and let's hear your talk.
Hello, my name is Itauma. I'm a computer science instructor at Wayne State University, Detroit, Michigan. And today, I'm going to be speaking about a research in unsupervised learning and image classification in HPCC. This is a project that was done while I was a master's student at Wayne State University. This project was also published at the International Conference for Machine Learning and Application in 2015. So here are what we are going to look at. We're going to be looking at during this presentation. I'm going to take you through the whole project pipeline. You may already know that image analysis can be done using HPCC systems, and that an image or an RGB image, when converted to a grayscale image, is simply a very big matrix, which when converted to a transposed to a vector can be treated like any other data set. This project was done in the Data Science and Analytics Lab at Wayne State University under the supervision of Dr. Zoen Chen. And we also had the opportunity of collaborating with the organizers of this program. The objectives of this project was to speak to the machine learning community at the ICMLA conference that there is a wonderful platform called the HPCC systems that can be used by machine learning researchers and can also be used for image classification. And so we explored feature representation from face images and sound data and classification based on the representations. Here is a description of a diagram of the HPCC architecture. And here you can find here we have the system configuration that we use. We use a single node HPCC system. And before you explore big data analytics, the first thing you must consider is the size of your data. And you must also consider if the size of your data would fit into the available RAM that you're utilizing. And so that was the first thing we have to contend with. And I was using just a single node. And the goal of this project was that I was trying to compare the results of some works in the literature by Quartz et al. And see that I can do follow the same pipeline and implement the whole program in HPCC using the ECL programming language. Here's a general architecture of the HPC systems. So our major contributions are for this study, the use of HPCC platform in the implementation of the feature learning and object classification tasks, a feature learning and recognition framework using a multimodal strategy. This idea utilizes the HPCC platform to handle identity recognition using multimedia data in a multimodal framework, which leads to high recognition accuracy. By dividing a face image into several subunits, we can extract intra-region information more precisely, and this leads to much higher classification accuracy. So here is the pipeline for the project. And so we go from the unsupervised learning, where we're trying to learn good feature representations from unlabeled data, which can then be utilized to improve the accuracy using various classifiers. So in this project, we made use of the HPCC systems ECL machine learning library, which is freely available. So we made use of all the algorithms that is available. For classification, for unsupervised learning, we utilize the k-means clustering algorithm. And then for classification, we explored various classifiers like naive Bayes, random forest, decision tree, etc. Now, the first task in this work was to consider how we're going to read images into HPCC. And like I said earlier, that an image is basically, a grayscale image is a big matrix. And so we decided first, as you would see here, we have a colored image. We converted it first to a grayscale image. And what the computer sees is a bunch of pixel or intensity values of the grayscale image. And all these images were resized to a similar dimension. So take, for example, 50 by 50. And this matrix was then converted to a vector. So we have in this case, we'll have a 1 by 2,500 vector. So given three images, then we would have a 3 by 2,500 matrix, which is written to the CSV file. And this CSV file is then sprayed to HPCC. So feature learning. The goal of unsupervised learning is to find a lower dimensional projection of the unlabeled data that preserves all the information in the data while reducing redundant dimension. We utilize the k-means clustering algorithm in this task, which is similar to the work done by Quet et al. Now, after performing unsupervised learning, here's a visualization of the length weight using the AR face data set. So from this diagram, you can see some features were actually learned after running k-means clustering algorithm. And for classification, we explored various classifiers such as the decision tree, random forest, naive Bayes, and softmax. So in machine learning, all classification algorithms follow three logical steps: learning the model from a training set, testing with respect to obtaining measures of how well the classifier fits, and classifying, which involves testing the model on new data in order to compute a classification accuracy. So that was the model that we followed. And here's an example of the AR data set. And in our work, we explored utilizing regions of interest like the left eye, the right eye, the nose, and the mouth. We generated various data sets which we compared. And here are some results that shows that HPCC systems gives comparatively good results as other platforms like implementations using MATLAB, Java, etc. Now, on this slide, we found something very interesting. So using the different features, data set that we created from the left eye region, the right eye, the nose, and the mouth, you can see that the right eye had a recognition rate of 77.1%. And so we were saying in the lab that, wow, so that means I can identify you from your right eye, basically. And using the multimodalities, when we combine the left eye, the right eye, and the nose and mouth, we're also able to improve the accuracy of classification. And for this, we explored using the public figure data sets. There are about 83 public figures, but we reduced it to 10 subjects based on the fact I was working on this with a single node cluster. And we made use of 100 images from each of the subjects. And also, for this, we also explored using the audio data of each of the subjects in order to create a multimedia data set. And in this result, in the lower end, using the decision tree classifier, using the multimedia data set, we had a much higher accuracy. So our observations are, feature learning and object classification was successfully performed in HPCC. We utilized a single node HPCC platform, and the decision tree classification method achieved higher accuracy compared with various alternatives or other classifiers. Now, here's a relation that we also observed. We observed that when we increase the number of features, the accuracy also increased, and so did the running time of the algorithm. And using the decision tree algorithm, we also observed that when we increase the depth of the tree, at a particular point in time, the accuracy stops increasing, so it remains the same. However, the running time increases, and so we know where to stop in terms of the depth of the decision tree. And the implementation code for this project is available on GitHub. So in conclusion, this study demonstrates feature learning and object classification problems in HPCC with faster optimization, calculation of algorithms, and low cost of hardware. Several databases with image and multimedia content were explored in HPCC. Our learning framework leverages new representations that are learned over multimedia data automatically. We observed that the decision tree classification algorithm boosts recognition rates compared to other classifiers, and this identity recognition algorithm can lead to further exploration of face recognition problems. And at the ICMLA conference, we're able to discuss this to other researchers, that they should use the HPCC systems for their research. The next steps are setting up a multi-node HPCC lab for big data processing, exploring teaching ECL with a focus on matrix computation, and then explore more machine learning applications using HPCC. Here are my references. Thank you so much for listening. Please feel free to ask any questions during the lunch. Thank you.
Thank you very much, Itauma.
Thank you.
I apologize for not taking questions now, but we want to move quickly to the next presentation. This was a very interesting presentation, particularly the fact that you can improve the accuracy by just segmenting the image into components. I thought it was quite interesting to use that type of methodology. So I think there will be quite a few follow-ups with him later on today. Anyway, now the next couple of presenters, if you deal with networks, and some of you might deal, I'm talking about social networks or graphs, there are some challenges there. Well, you might deal with a network with categorical values, and that might be kind of easy. If you make them continuous values, it makes it harder. And if your network has only a few dimensions, it might be okay and probably compute easy or light. But if it has tons of dimensions, it will be hard. So our next presenters, Kshitij and Syed, will be talking about these high-dimensional networks with continuous variables. I hope you will enjoy this talk too. Thank you, and Syed and Kshitij.
Thanks, Flavio. As Flavio mentioned this morning, this is my second community day. I was here last year too. And honestly, it was quite refreshing getting out of the academic cocoon and coming here and listening to a diverse set of interesting talks and ideas. And this year has been great too. So as Flavio mentioned, one of my primary research interests is high-dimensional covariance estimation or network estimation. And my doctoral student, Syed, he did an internship this year implementing one of our algorithms in ECL. And that's what the talk today is about. Last year, before I was preparing for the talk, David Bayliss, who is a mathematician himself, among other things, advised me that this is not a math department seminar, and I should keep that in mind. And I haven't forgotten that advice this year too. So, our main goal in the next few minutes is to really convey to you three things. One is, what is high-dimensional network estimation, and why is it important or relevant or useful? The second is roughly what our algorithm is trying to achieve. Okay? And the last thing is why we thought that ECL or HPCC was an ideal platform to implement this algorithm. All right. So I'll get started with an overview of high-dimensional network estimation. And some of this material I talked about last year as well, so it might be familiar to some of you. So what has happened in the last 1 or 2 decades is suddenly we have what we call as high-dimensional data from almost all sorts of applications that you can think about. And in statistics, when we say high-dimensional data, we are thinking about data sets where the number of features or variables, which we denote by P, is in the thousands or hundreds of thousands, so very large, but the number of samples or repetitions that you have is pretty small in the hundreds. So number of samples is denoted by n. So if you hear a statistician or data scientist saying, I have a large P small n data, or I have a large P large n data, that's what they're talking about. Huge number of variables or features, but very small sample size or very small repetitions. All right? And examples abound. You can think about microarray data sets in genetics where you have data on hundreds of thousands of genes, but only a few patients. Or you can think about some financial data sets where there is data on thousands of stocks, but only a few time points. Right? So what are we trying to achieve here in these applications? A common goal in most of these applications is to understand the often very complex network of relationships between these features, so between stocks or between genes or between environmental locations, right? That's a common goal. And if you want to do that, the most fundamental quantity that captures the relationships between a bunch of features or variables is their covariance matrix. So even if that's not your end goal, that's a very good place to start with, okay? So the objective here is to estimate the covariance matrix of a bunch of features or variables, right? And a quick recap, what's a covariance matrix? Well, if you have two variables, the covariance between them is a mathematical quantity which captures the linear dependence between these two quantities, right? And positive covariance means similar behavior, negative means opposite behavior, 0 means there is no linear dependence, right? So this is just a toy example. If I have 5 stocks, let's say, then their covariance matrix is going to look like a 5 by 5 matrix, right? So the 4,2th entry of this matrix will be the covariance between the 4th stock, S4, and the 2nd stock, S2, right? So you can build a matrix like this. Now imagine a situation where you have 1,000 variables, okay? 1,000 stocks or 1,000 locations, 1,000 genes, okay? So I now have a 1,000 by 1,000 matrix of unknown parameters that I would like to estimate. So it's a symmetric matrix, so still roughly you have 1 million unknown parameters that you want to somehow estimate from just 100 repetitions, or maybe 200, a few hundred, doesn't matter, right? Sounds like an impossible problem, Million or billions of parameters, I want to estimate them from a few hundred replications or repetitions. And it has been theoretically and practically shown that all the classical estimators or tools that statisticians had for this problem, they performed really, really poorly in these sort of modern settings. Okay? So the question is there a way out here? Well, clearly there is no magic pill here. Like I have billions of parameters and somehow magically I'm going to estimate them correctly using only a few hundred data sets. So statisticians and data scientists struggled with this for a long time, and one very simple and logical idea somehow succeeded in breaking the barrier. And the idea is this. You have a few resources, right? Focus them on estimating the most significant parameters, okay? And assume that all the other parameters are so insignificant that you can just think of them mathematically as 0. Okay, so that's the idea. You have a large number of parameters, only a few resources. Assume that only a few of these parameters are significant and focus your resources on estimating them. And just all the other parameters are just 0 mathematically, right? That's the idea. Very simple idea, but very far-reaching. Okay. However, as simple as it sounds, there is still a lot of challenges left. Which parameters do I assume to be 0? So I'm talking about the covariance matrix now. Do I assume which covariances I assume to be 0, or should I deal with the inverse covariance matrix and assume that there are zeros in that matrix? So which parameters to assume to be 0? That's a very important problem here. And second, the problem is to build a principled statistical model which can be analyzed and which has good theoretical properties. Okay. So, all right. So where does network or graph come into this picture? Right. I told you I have a matrix, and I'm going to assume that some of its entries are 0, and I have a way of choosing that. So this pattern of zeros that I'm going to impose on my matrix, and I'll show you an example shortly, that can be encoded in terms of a network or a graph. Okay, that's where networks are going to come in. So just bear with me for one more slide. Right. So here is what I'm going to do. Right. Last year, the talk I gave, we worked with the inverse of the covariance matrix, and we assumed that a lot of the entries in the inverse of the covariance matrix can be set to 0, and we are going to focus our resources only on estimating the few significant entries. Right. This year, I'm going to talk about another problem. So what we're going to do is, so sigma is the statistical symbol for the covariance matrix. Okay? So I want to estimate this covariance matrix sigma. That's my problem with very few resources, right? What we are going to do is first, we are going to transform our covariance matrix into what is known as its Cholesky parameter. So it's a well-known mathematical device. The only two things I want you to take away from here is, given any covariance matrix, you can do a simple transformation to get a lower triangular matrix, and that's shown in right here. Okay, so this matrix L here is a lower triangular matrix that you can get by doing some transformation on the covariance matrix. Okay, and estimating the covariance matrix is equivalent to estimating this Cholesky transformation, whatever it is, right? And just as the entries of the covariance matrix have a very practical and direct interpretation in terms of the underlying features, the entries of this Cholesky matrix also have a very concrete interpretation in terms of the underlying features. So it's basically a mathematical device or a transformation that I have used depending on the application to simplify my life. Okay? All right. So now, here is where the graphs are going to come in. Okay? So I want to estimate my Cholesky matrix L. That's equivalent to estimating the covariance matrix sigma, because it's a one-to-one transformation, right? So let's look at this simple case here. Let's say I have 4 features or 4 variables A, B, C, and D. All right? So if I look at their Cholesky covariance matrix, I have a lower triangular matrix given by this L here. So the upper triangle is always 0 in the Cholesky matrix, so we can ignore that. Now let's look at this lower triangle here of this matrix, right? You will notice 2 zeros. The B, C entry is 0, and the A, D entry is 0, right? So let's say that after doing some analysis, I decided that I'm going to treat these 2 entries as insignificant, and so I'm going to mathematically set them to be 0, right? So that's my sparsity pattern, that the B, C entry and the A, D entry, I'm going to treat them as zeros, and I'm going to focus my energies on estimating all the other entries in this matrix, right? Now, this pattern of sparsity can be very nicely and conveniently represented in terms of a directed graph here. Okay? So how do I construct this graph? Well, I take my variables or features, and I put vertices corresponding to them. So I have a vertex for A, a vertex for B, C, and D. Okay? Then I put directed edges from each vertex to the other vertex, where direction always goes from the smaller vertex to the larger vertex. So A is smaller than B, so the directed edge is always going to go from A to B. Okay? And then, whenever I put a 0, whenever I choose a certain entry to be 0, I just remove that edge. So you will see that in this network, because I have chosen the B, C entry to be 0, the edge corresponding to BC is missing. Because I have chosen the A comma D entry to be 0, the edge corresponding to A and D is missing. Okay? So every sparsity pattern in my matrix that I'm trying to estimate can be equivalently and very conveniently represented in terms of a directed network. That's where networks and graphs come in the realm of covariance estimation. Okay? There is a very nice and direct relationship. And so what is the statistical challenge? As I was saying before, so you have this data set, very few repetitions, large number of variables. You have this big matrix that you're trying to estimate. And your method of attack is assume that a lot of its entries are actually insignificant and can be set to 0. The problem is, how am I going to estimate this pattern of zeros from the data? All right? And so I will just briefly tell you how we are going to do it. This is what we are going to do is we are going to construct a cost function or objective function, okay, over our matrix. Okay? And this is a standard technique in machine learning, which is your cost function has two terms. One term comes from the data, the likelihood of the data, and the second term comes from is called the penalty term, and the function of this term is to give you answers which are going to have a lot of zeros in it. That's what we want. Okay? So roughly that's what we do in a standard technique in machine learning to get these estimates which have lots of zeros in them. All right? And so this is the cost function that we have, and we are going to optimize over this cost function and generate an estimate of the Cholesky factor and hence a covariance matrix, which is going to have very few significant parameters. Okay? Last thing I want to note is in this cost function you will see this parameter lambda here. Okay? That's something that the user can choose. Suppose you have a data set and you know that you want a lot of zeros in your ultimate estimator. You're going to choose a very large value for this lambda. If you don't want so many zeros, you choose a small value for this lambda. So the lambda is a user-dependent parameter which can be used to control the amount of zeros that you want in your ultimate estimator. All right? And I'm going to let Syed continue and tell you about how he implemented the algorithm in ECL.
Okay, so essentially the cool thing about the objective function of the CSCS function is that it breaks up as an independent function of the rows of the L matrix that we're trying to estimate. Now, why is this important? Consider a function f, which is a function of x, y, and z. If this, we can break up into a sum of f1, which is a function of x, f2, which is a function of y, and f3, which is a function of z. What we can do is just focus on f1, f2, and f3 independently, right? Minimize each of these, and then we'll have the minimum for f in that way. Now, this is where ECL comes in, because this means that we can focus on each row of L independently and do them in parallel, right? And now I'm going to talk about applying this in ECL to a call center data set. So the data set is from the call center, and basically there are calls coming into this call center for 17 hours a day, and we divide that into 102 time periods. Each time period is 10-minute long, and basically you record the number of calls. We did a singular value decomposition to basically screen out the outliers, and we're left with 239 days. So we have n equals to 239, and p is equal to 102. That means that we have about 10,000 parameters in the covariance matrix that we want to estimate, right? Because it's p choose 2. Now, our goal is to build a predictor to forecast the calls coming in during the second half of the day using the first half of the day, okay? So what we're going to do is basically use this thing called the best mean squared error forecast. It essentially minimizes the mean squared error, and it turns out to be YIT2. That's the number of calls coming in to the second half of the day is a function of mu2 plus sigma 2, 1, sigma 1, 1 inverse times YIT1. That's the number of calls coming in during the first half of the day, and we have to subtract mu1 from this. Now, what we need to estimate here is mu2, mu1, sigma 2, 1, and sigma 1, 1. And we're going to do this from a training data set. So first, we divide the data set up into two parts, a training data set and a test data set, because we want to evaluate the performance, right? We're going to compare the performance of the estimate we get from CSCS to the standard estimate, which is the sample covariance matrix. And to do that, we divide up into a training data set, test data set. Our training data set has days 1 through 205, and a test data set has days 206 to 239. So from the training data set, we get the estimates from mu2, mu1, and sigma, and then we basically compare the observed and the predicted from the test data set. We take the absolute difference, sum it up, and then take an average, okay? And the last thing for CSCS that we need to do is pick the lambda parameter, which my advisor spoke about, and we do this using fivefold cross-validation. It's a standard technique in machine learning. I can talk more about that later if someone has questions. And here we have a plot of the performance, right? In blue here we have CSCS, and you can see that CSCS outperforms the sample covariance matrix 46 out of 51 times. So it has a lower absolute forecast error 46 out of 51 times, which means it's far superior to it, the sample covariance matrix, okay? Finally, a timing comparison between a parallel and a non-parallel version, and you can see that the parallel version is about 40 times faster than the regular version, with like around 50 nodes. So this is, it's a testament to how ECL can really help you take advantage of parallel algorithms. Finally, here's some code. So this is the basic code for the cyclic coordinate-wise algorithm. So this is working on each row. Some ECL code here. Not the whole thing, it's just like a chunk of it. This is the CSCS algorithm. The important part is that you can do this in parallel, and essentially this is the ECL code that does it. So S is the matrix that needs to be in all the nodes, so that I distribute that over all the nodes, and then L is a matrix, but it has an added record set, basically, which has the node ID, and I spread that out over the individual nodes. So basically, you can run the operations in parallel. Okay, I guess that's about it. I'd like to thank John Holt for allowing me to work on this, and Lorraine for taking care of the logistics. Thanks very much. I think we're going to end right here, right? And we'll take questions later on. Yeah.
Thank you. Very good. Thank you. Okay, that was a very cool talk. I really liked it, and I think that there will be other interactions probably around that later. Looking at the camera now, we have our live streaming, so I hope people are still sticking there, watching this live streaming. We have plenty more things to come. Our next talk is let's do a quick quiz here. If I ask you people in the audience if you know what I mean when I say random forest, raise your hands. How many of you know what that means? Quite a few of you. What if I do tell you about sparse autoencoders? How many of you know what that means? Okay, some of you do. Very good. So, and I hope those that are going to talk now know about that because they have actually developed that for ECL and HPCC. So I want to welcome now Maryam and Victor Herrera from FAU, who will be talking about unsupervised and supervised learning on HPCC. Please help me welcome.
Good afternoon, everyone. My name is Victor Herrera. I'm a PhD student at Florida Atlantic University. And today, along with Maryam, we're going to present a brief look of our work. So we've been working in a cooperative research project between LexisNexis and Florida Atlantic University for a while. And actually, the goal of the project is to implement machine learning algorithms in HPCC system platform. I will start presenting my recent work optimizing supervised learning methods. First, I'm going to talk about the optimization of random forest, and then I'm going to talk about sparse data working with a naive wave classifier. So random forest is an ensemble supervised learning algorithm for classification and regression. Basically, it builds a bunch of decision trees. These decision trees are special because the split on each node is done only with a subset of the whole features. There is a process that randomly selects a subset, and it split the data based on that. The classification part is done also in parallel. I'm going to explain later. So the random forest learning process is based on the decision tree recursive partition principle. Although in ECL, recursion is not allowed, the recursive partition was implemented in ECL in an iterative way. So it is an iterative split partition process, uses the built-in function called loop. Our initial implementation of random forest wasn't far for being effective, and actually it wastes too many resources by sending both independent and the dependent data set for all the samples to build the tree to the loop body function. And the implementation was not fully parallel as well. So we review our initial implementation and, and we reorganize all the code. So we reduce the size of the record set sent to the loop body function by passing only the dependent data set, and inside the loop, fetching the independent data required. Now remember that only a subset of the whole features are required for each node independently. And also, we fully parallelize the loop body function in order to receive only the dependent data set. Here we can see our results on a preliminary exploration of the optimization. It was completed with the help of Vivek Nair. I don't know where you are. Yeah. Last year, and actually we found out that the new approach that it is fetching the independent data from inside the loop body from an outside data set was a success. So we optimized the whole random forest learning process, and then after that figure out that the classification could be done as well in an iterative process. In the beginning, it was doing through the DOPS operation, but it wasn't efficient as well. So we turned into using an iteration way, and it worked well. In this graph, we can see only a little change. I mean, actually, we were using only half the features for make the experiments, but after the whole implementation was completed, I can tell you that the ratio of the runtime reduction is related to the ratio of the feature selected and the complete number of the feature from the training data set. And now I'm going to talk about working with sparse data and naive Bayes. So basically, a sparse matrix is a matrix that have a lot of zeros or default values, in the matrix. One way to reduce the amount of memory or disk to represent the data is to only take care of the non-default values. So you can watch on the screen that this matrix of 15 elements can be represented only using 7 records, because there is only 7 non-default values. So we implemented a new version of naive wave that can be fed with only the non-default values and make all the calculations on the frequencies of the default value using the count of the total instances of the training data and taking a complement with the non-default value. So instead of counting this amount of 0, that it doesn't have to count something that you know how many there are, just a difference, we can reduce both the learning process and also the classification process. And we did some experiment using a very big data set from a sentiment analysis, basically a bag of words. So there were 1.6 million instances with more than 100,000 features. Actually for each, it comes from Twitter. For each Twitter, only a few words were using, but the vocabulary was very big. So this data was highly sparse. So we first trained the data and classify everything with the FAT data set, and actually only using 5% and then 20% or 50% of the size of the training data. We took from 1 hour until 12.5 hours to complete the process. In contrast, using the new naive wave sparse with FFF data, we reduced this time to 70 seconds. So even though we can, after that, make a cross-validation tenfold in minutes. So the reducing on the time depends on the sparsity of the data set, and it really works, actually. So summary, I present my work on optimization of random forest, both for the learning process. I didn't explain the classification process, in detail because the time, and also my work using sparse data with naive wave classifier. Now, Maryam, I'm going to explain her work.
Thank you. Hello, everybody. My name is Maryam. Today, I'm going to be presenting the works I have done and the algorithms I implemented on HPCC system toward having deep learning and deep networks on this system. First, I'm going to talk about the optimization algorithm I implemented, then the implementations I did using that optimization algorithm. Mathematical optimization is when we want to minimize or maximize a function. For example, here we want to find the minimum. And optimization algorithms are the heart, or you might say, most practical machine learning algorithms. For example, in linear regression, you want to minimize the errors. In support vector machine, you want to maximize the margin between your support vectors. In many other fields in machine learning, you can see optimization algorithms being used. And how it works, it's that you formulate your training as an optimization problem. So you have your parameters that you need to learn, you need to train. You define an objective function based on those parameters. Usually it has 2 terms. And then you use an optimization algorithm to find the values that minimizes that objective function. And in previous presentation, we had this objective function and this minimization as well. So how the optimization algorithm works? They start with a random point, and in each iteration, they try to move forward toward your minimum point. What happens is, in each iteration, you need to know in which direction you want to move, which is called search direction, and how long you want to move toward that direction, which is called a step length. A simple algorithm like gradient descent decides to use a constant value for a step length. The problem is you need to tune this value for the application you're using. If you use a small step length, it takes a long time to converge. If you use a large step length, when you're close to your minimum, it overshoots you from the minimum. So that's the problem. And another thing is the search direction. You're just using negative of gradient. You're just using first order derivative information, which is the green path. You're not taking advantages of curvative information, which is the red path, and gives you a faster route toward your optimum point. So what I implemented is called LBFGS algorithm. It's actually limited memory version of the original algorithm BFGS. So for this algorithm, you don't need to tune any step length. At each iteration, the algorithm finds a step length that gives you a sufficient decrease in your objective function, as well as making sure this step length is not too small. And also, for search direction, this algorithm takes advantages of curvative information. It uses Hessian matrix, which is actually the second order partial derivative of your objective function. And this algorithm is called limited memory, which makes it very good algorithm when you have large problems. By large problem, I mean when you have lots of parameters to learn, which is the case in neural network. In deep learning, you simply can have thousands or millions of parameters. So this algorithm, instead of keeping an n by n matrix in memory, which n is the number of your parameters, it actually keeps a few vectors of length n. That's why it's perfect when you have large number of parameters. And as I said, it's more stable considering the learning process, because you don't need to tune any step length, and also it uses curvative information to have a more direct route toward your optimum point. How you use this algorithm? What you need to do is, for any specific machine learning task that you have, you need to formulate it to an optimization problem. You define your objective function, and that this objective function at each given point calculates the objective value and the gradient based on your training data. And if you're having a supervised method, your training label, you provide this function to LBFGS algorithm as an input, and it does the rest for you. It does the training for you by finding an optimum point for some values that actually minimizes your objective function. Based on this scenario, I have implemented a sparse autoencoder and softmax classifier using this scenario for using a LBFGS algorithm. Sparse autoencoder I implemented because by stacking them a sparse autoencoder neural networks, we can have a deep network. And what is a sparse autoencoder? It's a neural network when your output is the same as your input, so it's an unsupervised method. And sparsity comes from having your hidden layer nodes most of the time being inactive. And it has been shown that this sparsity extracts for us better features that you will see later in the slides. And I formulate this problem to an optimization problem. I did the training, and here you can see the results. I provided 10,000 samples, randomly selected patches of size 8 by 8 from images like this. And these are the features that were extracted by a sparse autoencoder. It was able to extract edge detection features in different orientations. And I also provided MNIST dataset, which is a handwritten digit recognition dataset to the algorithm. And the algorithm was able to extract these digit-like features. And another algorithm I implemented, again using LBFGS, is softmax regression, which is a generalization of logistic regression when you have more than 2 classes. For example, in MNIST dataset, you have 10 different classes. again, I formulate this to an optimization problem, and applying these softmax on MNIST dataset, I was able to get 96% accuracy. All the implementations I have done by now are toward having finally a deep neural network in HPCC systems, and you can stack up your sparse autoencoders and have a greedy layer-wise training in order for initializing your parameters. Then you can have the softmax as your supervised layer on top. And again, you can do the whole network. You can fine-tune it, again, using LBFGS algorithms. So you can see through all these implementations how important optimization algorithms are. During my implementations, I definitely took advantages of what HPCC system is providing. I used the PBBLAST library, which is a great library for doing linear algebra and all the matrix multiplications, computations you want to do. It allows you to partition your matrices and do parallel analysis. For example, imagine you have two very big matrices you want to multiply. By using PBBLAST, you partition these matrices, and you have your corresponding partitions in this ending up in the same node, and then all these multiplications can be done in parallel, and then at the end you aggregate the whole to have the final matrix computed. And also, one other great feature that HPCC system provides is using graphs. By following and looking at the graphs, you can see how your data is flowing and how long each job is taking to be done. And it really gives you a good idea how you can make your algorithm works faster. As summary, I want to emphasize again how optimization algorithms are important for having advanced, for implementing advanced algorithms, such as having deep learning. So I think optimization algorithms are really something we need to work on. And as I said, LBFGS is implemented. We can use it to implement other algorithms, such as other deep learning algorithm, convolutional neural networks, and hopefully by all these implementations, we're moving forward for having deep learning and deep networks on HPCC systems. And I would like to thank John Holt, the creator of a great library, PBBLAST, and all his helps when I had any question. And thank you all. Thanks.
Thank you very much. Great talk. Thank you, Maryam. Great talk. This is good. So if you didn't know about sparse autoencoders before, now you know more about them. And also exploiting sparsity to increase performance on a 40-fold basis sounds quite impressive. So that's very cool. But now, to end in a really, really, really high end, if you are a sports follower and you like to watch games and predict and maybe do some football gambling in fantasy football out there, not that I encourage to do that, we'll have a great talk from Vince Freeh from NC State, and he will be telling us about his new football scoring prediction on HPCC. So, Vince.
Hi, thanks for, I'm going to try to not keep you from your lunch too long. I know I get the unenviable position of keeping you from the lunch, but I really want to thank you for the opportunity to talk here. I really enjoy this. One of the things that I think is really neat about HPCC systems and together is that the attention to detail. I mean, we get this great audio to introduce you to introduce the speakers, but it carries throughout the entire system. I echo what Raj said earlier, that when he was looking for something, he said, somebody had a problem, he went to ECL and he found it. I find that with when my students and I are talking, we say, wouldn't it be great if they have this? Well, now I don't say that anymore. I say, I'm sure it's implemented, just go find it. So it's really nice to be able to work with this system. So I'm really happy to do this. Okay, so let me go ahead and tell you that I'm not the major player in this system. I had a lot of help from several people, some of the people in this room, and some risk system, and a few students at State. I'm going to give you a quick background to help you set up what's. I'm a computer science in the computer science department at NC State, and my background is distributed systems. I started off doing MPI, message passing interface, for high performance computing of the DoD style stuff. I then, my last PhD student did some work in Hadoop to do some auto tuning of some parameters to make sure that you could run the Hadoop a little faster. My current PhD student is doing work in HPCC. So I'm evolving in the right direction. Anyway, so as that background, my department had asked me to create a course that I called Data Intensive Computing, because we have a real demand within our profession for this kind of skill. And you can tell because students will sign up for this class immediately. We have the way our registration works is kind of like an e-commerce site. You put classes into your shopping cart, and then at some time at 8 o'clock in the morning, some day during the semester before, registration opens and everybody has to go in there and press checkout to get their classes. Well, this semester, 45 students enrolled in my class, and about a dozen came into me the first day, and they said, how can I get into this class? Because I clicked the button, and I must have been a few milliseconds late. So there's a real demand for this class. And so two things to take away from that is that there's a lot of people who know that what you're doing is important, and I'm a great instructor. So those are the two things to remember from that. So, the other thing I want to tell you is that whenever I look at when I first started HPCC, I was looking at examples, and they were either really simple, which is somewhat unsatisfying, or they were a little more complex and they required a lot of domain knowledge. And so Jesse Shaw has a really good way of explaining about fraud detection. It was really neat. He was showing how he found patterns in fraud. But I don't know the difference between patterns in fraud and just irresponsible behavior. So I wasn't able to figure out why this was significant. So what I wanted to do was pick something where the domain knowledge was fairly prevalent. Maybe not in this setting, but if you go into my neighborhood, everybody knows about football. And so it seemed like a really good way to try to make it more accessible to the community. So the other problem I have in the class that I teach, this data intensive computing class, it's a project oriented class. I have my students get together in groups and they do a semester long project. And it turns out that they pick Hadoop about 10 to 1 over HPCC. Even though I try to be agnostic about the platforms, but I do have an interest in HPCC that I let them know about. But they still pick Hadoop. There's a lot of reasons why, and I don't blame them. They're there to get jobs. It's a professional master's degree. We have a lot of students in there, and they want to pad their resume with being able to say this, and it makes a lot of sense. But I wanted to see if I could try to make it a little better for them. So one of the things we did was we decided that what I would do is I would build this system, which again has some domain knowledge that makes it a little easier to understand, but I would also package it up in a VM, which we would then distribute on our internal cloud, which all students and faculty can use at NC State. And so they could just pop up a virtual machine, have an instance of Roxy and Thor and Roxy running with the data set already on it and the code, so they could immediately start playing with the data. So we thought that this might be an interesting way to get them started on this. All right, so so the way it works is we parse the data, we find it online, and we grab this data, we parse this thing, dump it down, do this with Python front end. And then we take the data and we upload it into the HPCC cluster. You all know how this works, right? And then we run some analytics on top of that. So I'm going to work backwards to the front, because that's from the end product, because that's the more interesting way to talk about this. So what we did was I was encouraged to use Kel to model this, and I know all of you have heard about Kel, but if you haven't used it, I would really like. I just want to say you should use it, because it's really neat, because Khare has entities and associations, and I like to think of them as like nouns and verbs. If you have nouns and verbs, you can say anything you want. If you have entities and associations, you can model anything you want. And so I don't know if that's the way that David Bayless would say it, but that seems to resonate with me. And so so that's the way that I like to look at Khare. And so I got a chance to use Khare, and now I'm not even dangerous with Khare. I'm just barely scratching the surface. I think I kind of understand what it does, but there's so much more I'd like to learn about it. So the other thing is I want to talk about football. The reason I chose NFL football is because it's discrete. It's easy to model. It's unlike metric football where you're kicking the ball around. You can't really say you can't describe a situation very well. But with American football, you know exactly where every play begins because the ball's placed down. There's a time when it begins. You know the score and you know the down and distance. So it's a very discrete kind of. So this is an example of a game where the Carolina Panthers were playing, where they had an 8-play drive that ended in a touchdown, where Cam Newton throws a touchdown. So I don't know if you picked up that signal, but some of you guys who watch football might have understood that. So anyway. What it is it's a simple series of plays. So we can now look at football and model it as a distinct set of plays. This is really simple. This really simplifies your analysis because you can absolutely say what the situation is. So here's an example of how I inputted the data. The bottom is just the CSV file that comes out of our parser. And this is for every one of the plays. And so these are the 8 plays in that drive. And you can see that I have all kinds of different fields in there, which isn't important right now. I'm not going to spend some time looking at that. And then we throw that into the ECL record. So that's the fairly straightforward part. Here was then the next thing, the real part where I needed a lot of help, and thanks Jesse for helping me out with this. But I was able to figure out how to model the NFL in a way that was very useful. So everything hinges on the play because the play is the discrete interval of the game. So the play belongs to a game, but it also belongs to a drive, which is a sequence of plays by the same team. And then the actions are anything that we can identify that a player did, such as a pass or a tackle. And so here's an example. You always have 2 teams in every game, and you have an average of 4 actions per play. So this is how the model plays out. Just to show you that just because I like code, I'm showing you some Khare code, but I don't expect you to read it. Here's the 5 entities in Khare, and then here's the 5 associations, and I think it's 6 files that we use to populate the entities and associations. So this is it. This is Khare, and this is the thing that that sets it up. This is the complete model. This is nice. I think this shouldn't be glossed over, even though I'm not going to spend a lot of time on it. The simplicity here and the way you can be explicit but understandable with what you're doing it shows a lot of the power of Khare. All right, so what I want to now talk about is sort of digress a little bit into football to give you a flavor of one of the analytics that we do, which I'm going to then talk about down the road, which is I think what a lot of people you've been touting up this NFL stuff, and I kind of geared this talk more towards the community, which is an HPCC community rather than a fantasy football league community. So, but I'm going to tell you a little thing that we did, which was calculate what we call the victory forecast. That's just the probability of victory at any point in time. So again, as a discrete point in time, I take thousands of these plays over a few seasons, and I put those into the system, and then I say whether or not the team that had the ball won or lost. And then that naturally falls into a logistic regression, and I can now figure out what the expected victory is from that play based on thousands of, it won't be thousands, but the numerous instances that are similar to that in the system. So it's basically about 5 primary variables that go into this regression that determine it. So just to give you an example of what's going on here, this is a football field, and so we're driving to the them field. And if you have a first down and 10 on the 25, and I apologize, when this went from my Mac to wherever it is, the line of scrimmage changed. So that should be the 25. But it doesn't matter because it's close enough. You have a first down and 10 on the 25, you have a 66% chance of winning if you're ahead by 3 points in the middle of the third quarter. Why is that? Well, because if you look at the data, 2 out of 3 times a team in that situation won the game. So now if you go a little further down the field, so you're 75 yards from the line of scrimmage, from the touchdown. If you go to midfield, you're 50 yards from the line of scrimmage, you're a little better off. So it improves by about 4%, and the same thing if you get down to the 25-yard line. Here's another example. This is in the beginning of the game. The score is tied, so I have about a 52%. I have the ball, though, so I'm a little bit better than a coin flip to win the game. So I have about a 52% chance of winning the game, and I'm on the 25-yard line. What do I have to do to not be worse on my next down? So I have to gain about 3 yards, have a 2nd down and 7 to have about the same victory forecast. And then on the 3rd down, I have to gain about 4 yards, so I have to have a 3rd and 3 on my next play to be about average. I'm not showing the next play because either I get a 1st down, in which case I'm better off than I was when I started, or I don't get the 1st down and then I'm worse. So there is no 4th play in this sequence. Here's another example, and this shows the power of data, I think. I didn't make this happen. This just it came out. So this is start of the 4th quarter. I'm ahead by 3 points, but I have a 4th and 8, so I'm going to punt the ball. I have a 60% chance of winning in this case. So I punt the ball, and then the other team now is going the other way. They have the ball with a 1st and 10, 45 yards further down the field, and they have a 40% chance of winning. They're behind by 3 now in this case because they're the other team. So what this says is that the complement of me sitting there at 4th and 8 is 45 yards downfield, a 1st and 10, the team taking with the ball the other way. And that's about an expected net average for a punt in the NFL. But I didn't have to write that. I didn't sit there and say, oh, they're going to punt on 4th down. The net average is about 45, so let's make sure these are equal. The data just says that. So it's really, I love working with data. I like it when data tells me what to do rather than me trying to tell the data what to do. All right, so given this VF, what can I do? I can do a lot of interesting things. Oh, sorry, that was the VF. Now I'm doing the middle part with this transformation. This is very simple. I just I take those CSVs and I transform them into flat files. I had to do a little bit of extra work because I wanted to annotate some of the data that doesn't come from the website, like the victory forecasts and stuff like that. And when I fetched the data, I just fetched it from multiple sources, and we compared the data. We didn't do anything fancy about comparing it, but when because they don't disagree that often, and when they do disagree, there's not that much data, so we're able to resolve that by hand. And just to give you an idea how much data we have, we create files called games, plays, drives, and actions. We create these files, and there's about 16 plays per week, 16 games per week, 256 games in the regular season. There's about 100. Well, there are 100 on average, 168 plays per game, 24 drives per game, and 4 actions per play. So it's not a lot of data. In fact, it's very tiny data, and using HPCC to solve this data is really a sledgehammer. But using ECL and Kel is not. It's just a good solution. I like using the declarative language ECL, and I like using Kel. So even though the Thor and the Roxy is a sledgehammer, the system is actually a good choice for this. Okay, so this is what my ECL watch looks like. You know what that? You all are familiar with that. Okay, so now let me just give you, for the last 3 minutes of the talk, I'll be able to tell you a few of the things that I was able to do with the victory forecast. So one of the things that I thought was interesting to figure out the top plays. I don't have to have somebody vote on this. I don't have to have ESPN commentators figure out what the top play is. I just let the data tell me which were the top plays. So this was the first week of this season, right? Yeah, week 1. So the first week of this season, we see what the top plays are. Well, the top 2 plays are missed field goals. Everyone who watches football knows that that's the critical play. Because you're sitting there, you're lined up for a field goal. If you make it, it's the end of the game. You make it, you win. You miss it, you lose. And so these are the situations where in the NFL, you're expected to make a 47-yard field goal. So when you miss it, it's a huge drop. And what's interesting is if you look at number 1 and then number 9, in number 9, they actually made the field goal. The time at the end, the point at the end of the game was a little different, so the numbers are don't quite reflect that. They're not perfect complements of each other. But basically, making the field goal only gives you a little bit of a gain, 24%. Well, that's in the top plays. But missing it lost you a whole bunch. And so you can look at that. So this is one of the things that we're able to do with this is to show some of the top plays of the game. The other thing I was able to do was look at a game flow for the whole game. And so in this case, I'm plotting the VF on every play. And I'm plotting that versus time of the game. And so what you see here is that Atlanta, our home team here, they won this game against Oakland. But it started off, it was a give and take game, and then you can see, now I plotted this for Oakland's victory forecast because they're the home team. So the negative is better for Atlanta. You know, the lower is better for Atlanta. And you can see how much they do. So this now gives me a thought. What I can do is I can look at that and I can say, how strong was this victory? So that gives me this thing called strength of victory, which is just trapezoidal integration of the victory forecast. And if you look at that, you can see that they vary quite a bit, from 92% of the available area in the San Diego win versus 28% when Tennessee won. And so what that looks like is, this is what San Diego looked like. They raced off to a big lead. They essentially ended the game in the first half, and nothing else mattered from that on because they had a huge lead. On the other hand, the Lions went out to the big lead, but then somehow they let it slip out of their grasp, and Tennessee won this game. So those were the top and the bottom from the previous chart. Well, looking at that, I then started thinking, you know what else I could look at is I could look at not just the strength of victory, but the competitiveness. That San Diego-Jacksonville game probably was pretty boring because San Diego had it in the bag in the first half. So now I'm just going to sum up the total cost of this strength of victory and figure out what's the most exciting game to watch. And in this case, it turned out to be Dallas and Washington. And if you look at that, you can see that it was nip and tuck. It went back and forth. Washington had a fairly strong winning percentage, and then they gave it the game away, and Dallas won at the end. All right, so, it just hit 0. So I'm done. Perfect timing. I'm out of time. What I want you to do is that the part that I didn't tell you was we also built a web server that talks to our Roxy, to the Roxy. So we built a complete solution because we wanted to teach that to all our students. So we have Thor, and then we deploy indices through Roxy, and we then serve up a web server that pulls the stuff out of the Roxy server. I'm going to have that up there sometime this afternoon when we have a break, and you can go ahead and look at it and see some of the stuff that I do live on that website. So thank you, Flavio.
Thank you. That was impressive, Vince, but I must confess that I got lost. I didn't get lost in any other session with any of the formula or anything, but the football thing just lost me. Okay, anyway, so that was very good. I love it. And I love the real-world use of KEL on something that is not necessarily anything specific that we have built KEL for in our own environment. So this is something completely different, a different problem domain, but a good use of KEL. So now